section 6.4, separable differential equations, page 4. All right, here we go. When a simple electric circuit containing no capacitors but having inductance and resistance has the electromotive force removed, the rate of decrease of current is proportional to the current. The current is I amperes 10 seconds after the cutoff, and I equals 40 when t equals 0, and the current dies down to 15 amps in 0.01 seconds. Express I as a function of t, estimate on your calculator, and confirm your estimate analytically. Oh my goodness. Is your head spinning? There is a whole lot of background information in here. When a simple electric circuit containing no capacitors but having inductance and resistance has the electromotive force removed, all of that is just background information telling you where this comes from. So all of that is not necessary to this problem for our purposes. What is important is right here, the rate of decrease of the current is proportional to the current. Rate of decrease of the current is proportional to the current. There's your rate of change. And we have I is the stuff we're measuring, so the rate of decrease of current, so di dt, is proportional to the amount of current, Ki. Now it's just like y's here. Instead of y's, you got i's this time, and that's okay. We're just going to go ahead and separate these variables here. I'm going to pull the dt up to the right and this I down to the left. So we have di over I equals K dt. And then let's anti-differentiate both sides. On the left-hand side, that's the natural log of I. And on the right, kt plus a c. And again, the stuff we're measuring, current, can't be negative, so the absolute value bars here are not necessary. And then let's take this just like we did yesterday, and we'll rewrite this. Well, it wasn't yesterday, was it for you? It was the previous page. So let's see, we have I equals e to the kt plus c. And then we can rewrite this as e to the kt times e to the c. Oh, and there's a constant again. So we have I is c e to the kt. Oh my, doesn't that look exactly like the one on page 3? Except we have a I here instead of a y. We started off with the same thing with a y, an I instead of a y. So here's the deal. From this point on, you may write this expression or that equation, that equation to start, di over dt equals ki, and skip all of this work in between and end up right down here. It is okay to jump through all that work, to skip all that work. But you need to be able to derive this equation if I ask you to. In this case, derive means to come up with the equation. Again, you must write that initial setup, then you can jump right to here. That's perfectly acceptable. All right, now let's go on to, we're still not at part A. We have this, I equals c e to the kt. So, some initial information. We know that at time 0, I is 40. Which gives us 40 equals c e to the k times 0. Can't talk right now. Sorry, that was my son calling me. I don't want to re-record this for that. Sorry. And this is just c equals 40. All right, now let's use this other piece of information. And the other piece of information that we have is that the current dies down to 15 amps in 0.01 seconds. So when time is 0.01, current is 15. You know what? I'm almost out of space. I'm going to rewrite this up here. Time is 0.01 when I is 15. And we'll plug that in, and we will have I15 equals C, which we figured out was 40, e to the k times 0.01. Okay, now let's divide out this 40. And 15 over 40, that's going to simplify down to be 3/8 equals e to the 0.01 k. And again, I'm going to show you both ways to solve this. Either way is acceptable. Okay, so we want to get rid of this 0.01, which means we'll raise both sides to the 100 power. Because 0.01 times 100 is 1. So this is just e to the k. And we're going to leave this right as 3/8 to the 100. Then your equation for I comes down to I equals C, 40. And then we're going to replace out that e to the k with that 3/8 to the 100. And then to the t, or times t. So we end up with 40 times 3/8 to the 100t. All right, the other way to solve this one is to rewrite this into logarithmic form, which would be the exponent 0.01k is log base e of 3/8, which is natural log. I'm going to multiply by 100 here, and we'll have 100 natural log of 3/8, which means when we go to write this equation now, we have I equals, same C, 40. This time we have e to the k. That's your k mess right there, 100 ln 3/8. And then that's times t. Yuck. I equals 40e to the 100t ln 3/8. Whew. Either format is acceptable. Okay, as I said on page 3, this way is probably what you're more familiar with in terms of solving for k, but your equation's ugly at the end. This one, a newer way to solve that equation, we solve for e to the k instead of just k, and your equation's much prettier. I like this one better. All right, part B, estimate on your graphics calculator the current in 0.02 seconds. So let me just put this up here. I've graphed, oh, so this is part A. I'm sorry, I forgot to say all that. That's part A, express I as a function of t. All right, now part B on your calculator. You are setting up y is 40 times 3/8 to the 100x. Here's your window. It's kind of hard to find this window, so let me tell it to you. It is negative 0.01 up to 0.03 for the x's, and y is between negative 10 and 50. When we graph, we see this, and we want to know what's happening at time 0.02. So time is 0.02, but time in our calculator is x. So we're just going to do a value. Oh, I'm so sorry, you can't see. I forget to check. I'm sorry. 0.02, and we get 45 over 8, which is I 45 over 8, which is, let's see, 8 goes into 45, 5 times 5 and 5/8, which is 5.625 as a decimal. There's the amperage. There's part B. Part C, confirm your estimate analytically. We're just plugging in 0.02 for time into our equation, so we get y is 40 times 3/8 to the 100 times 0.02. 100 times 0.02 is 3/8 squared. That's 40 times 9 over 64. Cancel the 40 and the 64. We can divide out by an 8, which gives us a 5 here and an 8 there. And oh, will you look at that? 45 over 8. Whew! Again, off the page. I am so sorry. Perfect. Thank you so much. I'll see you tomorrow with page 5.